Welcome back to The Explainer. Today, we're taking a really deep dive, a highly structured engineering journey right into the very heart of telecommunications. We're going to map out the foundational architecture of GSM, starting way up at the macroscopic level with those massive core network databases, and then we're going to zoom all the way in, right down to the microscopic logic of radio frequencies and logical channels. So if you've ever wanted to truly conceptualize how the grid keeps millions of devices connected simultaneously, you are absolutely in the right place. Let's get into it. All right, here's our roadmap for today's explainer. 1. Core network databases. 2. Security and network maintenance. 3. The GSM air interface. 4. Navigating traffic channels. And finally, 5. Broadcast control channels.
Section 1. Core Network Databases, the brains of the operation.
To really grasp how calls are routed and how your mobile subscription is managed behind the scenes, you've got to understand the specific databases that act as the true brains of the whole operation. To make the network function efficiently, engineers took subscriber data storage and divided it into two totally distinct components, the HLR and the VLR. Now, the Home Location Register, or HLR, that's your permanent, centralized network database. As long as you have a subscription with an operator, your core data lives right there. We're talking basic subscriber categories, allowed or barred services, authentication data, and your general current location. But here is the big so what factor. If every single call or text required the network to ping a centralized database that might literally be located in an entirely different country, the latency would be absolutely massive. The network would just collapse under its own signaling weight. So enter the Visitor Location Register, or VLR. The VLR is a temporary localized storage unit integrated right into each mobile switching center's service area. When your mobile device enters a new area, the VLR just downloads a complete copy of your necessary subscription details straight from the HLR. It's a brilliant localized architecture that prevents bottlenecks and keeps the network incredibly fast and responsive.
Moving on to Section 2, Security and Network Maintenance, Protecting the System.
Let's see how this builds on our core network model by shifting our focus for a second. We're moving from routing databases to how the network actually secures and monitors these vital connections. Security in GSM is largely handled by the Authentication Center, or AUC, and the AUC essentially serves dual protective functions. First up, it handles the subscriber authentication. By running this check, the network explicitly ensures that no unauthorized users can access the system. It basically acts as a super strict bouncer against anyone attempting to impersonate another user on the network. Second, it handles radio information ciphering. The actual information sent over the air between the network and the mobile station is mathematically scrambled or ciphered. This means your mobile station can only decipher the information specifically intended for it, which keeps your data totally secure as it travels over the open airwaves.
Now, what's really fascinating about this setup is how GSM fundamentally separates you, the user, from your physical equipment. Think about it. Your SIM card and your HLR profile authenticate you as a subscriber. But what about the phone itself? Well, that's exactly where the Equipment Identification Register, or IIR, comes into play. Because the subscriber and the hardware are treated separately, GSM requires a distinct, separate authentication process for the mobile station equipment itself. The IIR database uses the International Mobile Equipment Identity, you probably know it as the IMEI, to ensure that the physical terminal equipment is actually valid. So if a phone is reported stolen, its IMEI gets blacklisted in the IIR. That effectively turns the hardware into a useless brick on that network, completely regardless of whose SIM card is inside.
And tying all of these massive core components together is the Operation and Maintenance Center, the OMC. You can basically think of the OMC as the ultimate overarching remote control room. It physically connects to everything we just talked about: the mobile switching centers, the HLR, the VLR, the AUC, the EIR, and the base station controllers. It gives the network staff this centralized, computerized monitoring center so they can remotely control, diagnose, and manage the entire switching system network from one single vantage point. All right, Section 3, the GSM air interface, down to the airwaves.
So, leaving the macroscopic physical network behind for a minute, let's zoom way in, down to the microscopic logic of the air interface. When a signal is transmitted over the airwaves, it isn't just some chaotic burst of energy. It's highly structured into what we call logical channels. And these logical channels are strictly divided into two main branches: traffic channels and control channels. Traffic channels are essentially the heavy lifters carrying the actual user data and voice, whereas control channels are the invisible managers constantly carrying signaling and synchronization data. We're going to meticulously walk through both of these branches to see exactly how they function.
Section 4. Navigating traffic channels, carrying the data.
Let's start with those traffic channels. These are the dedicated communication pathways that carry your encoded speech or your user data on both the uplink and the downlink between a single mobile device and a single base transceiver station. Now, the crucial point for a full-rate traffic channel, which is designated as TCH, is the number 13. It is perfectly engineered to transmit full-rate speech at exactly 13 kilobits per second. To achieve this uncompressed, really high-quality audio transmission, a full-rate traffic channel has to occupy one entire physical channel on the air interface, all to itself.
But as any engineer knows, spectrum is incredibly expensive and it's highly limited, which is exactly why engineers developed the half-rate traffic channel. By applying much heavier compression algorithms, a half-rate channel transmits speech at 6.5 kilobits per second. This is just a brilliant piece of network design because it allows two entirely separate half-rate traffic channels to share a single physical space on the airwaves. By dropping that bitrate in half, network engineers can literally double the voice capacity of a cell during peak traffic hours, all without needing to install any new hardware or buy any new spectrum.
Which brings us to Section 5, Broadcast Control Channels, directing the traffic.
Shifting gears over to the control channels branch, we have the downlink-only broadcast channels. These essentially act as the lighthouses of the cellular network. They're sent out continuously from a single base transceiver station to every single mobile device roaming within its coverage area. Now, the very first broadcast beacon your phone looks for is the Frequency Correction Control Channel, or FCCH. You can think of the airwaves as a chaotic, incredibly noisy room. The FCCH transmits this pure, unmodulated signal. It's essentially a tuning fork. When your mobile station powers on, it listens specifically for this pure tone to help it accurately lock onto the exact frequency of the local base transceiver station. Without this specific logical channel, your mobile device would just be permanently lost in the radio frequency noise, completely unable to tune its internal radio to the network.
Right after your phone manages to lock onto the frequency via the FCCH, it desperately needs to figure out the timing. And that is handled by the Synchronization Channel, or SCH. This step brilliantly illustrates the absolute necessity of precision timing in telecommunications. GSM uses time division multiple access, meaning multiple users are actually sharing the exact same frequency by taking turns in these rapid microsecond time slots. To know exactly when to transmit without talking over someone else, the mobile device reads the SCH to get the current TDMA frame number. This frame number acts as the network's master clock, just constantly counting up, and it maxes out at exactly 2,715,684 before looping right back around. It literally keeps every single device in the cell perfectly synchronized down to the microsecond.
So, we've traveled all the way from the giant permanent databases of the HLR right down to the microsecond timing of the synchronization channel. It's an incredibly intricate, totally rigid system of circuits and logic. But looking at all these dedicated traffic lanes and pure tone frequencies, it really leaves us with a provocative engineering question. How exactly do these legacy circuit switch GSM logical channels and rigid security elements actually pave the way for the flexible packet switch architectures we use today in our modern 4G and 5G networks? It is a fascinating evolution of logic that we are definitely going to explore in a future explainer. Thank you so much for diving into the architecture with me today, and keep questioning how the invisible world around you is built.